Training the next generation of AI models requires hundreds of thousands of GPUs into vast warehouse-scale computing clusters. But operating at this scale creates a severe physical bottleneck. While the GPUs consume significant power, a second, less visible drain is the network itself. Routing a continuous flood of data between these servers requires its own dedicated energy budget. This image compares traditional cloud data centers against AI factories. In a 100,000 server cluster, transceiver power reaches 40 megawatts, consuming 10% of the total compute resources. Standard pluggable optics sit at the edge of the server board. To drive high-speed electrical signals across that physical distance of PCB requires energy that iterative designs can no longer provide. Solving this requires co-packaged optics, or CPO. By collapsing the distance between the compute silicon and the optical I/O, we can eliminate the transmission loss that currently drains the cluster. We can see this in action within Nvidia's data center hardware, which serves as the immediate benchmark for next-generation performance. This layout shows the central compute chip and its attached detachable optical subassembly. The annotation highlights the target performance, a throughput of 4.8 terabits per second. Surviving the AI Powerwall requires re-engineering the optical transceiver down to the atomic silicon level. TSMC developed a specific engineering stack to address this bottleneck, comprised of 3 pillars. First is silicon photonics for monolithic on-wafer manufacturing of optical components. Second is SOIC-X, providing ultra-high-density, bumpless die-to-die interconnects. Third is COUPE, the macro assembly stacking these layers into a single engine. To understand how data moves at 200 gigabits per channel without overheating the cluster, we must deconstruct this stack from the outside in. We begin with the Compact Universal Photonic Engine, or COUPE. This diagram shows the architectural separation of the engine. An electronic IC for logic and drivers is physically stacked directly onto a photonic IC. Placing the logic directly above the optics creates a smaller footprint and improves power efficiency, fulfilling the 3 performance metrics. External optical signals enter through the Fiber Attachment Unit, or FAU, in the top right. The signal passes through an anti-reflective coating and a microlens embedded within the silicon carrier, striking a pink reflector to bend into the horizontal waveguides inside the photonic IC layer. While COUPE manages the macro routing of light, its success depends on the microscopic electrical boundary where these layers are bonded together. Let's move down into the microscopic boundary layer to examine the interconnects between the logic and photonic dies. Traditional packaging uses microbonds, but their physical size limits scaling and introduces parasitic capacitance that degrades high-speed signals. TSMC's solution is SOIC-X, a 3D hybrid bonding technology that is completely bumpless. The face-to-back method shown here uses direct vertical hybrid bonds to distribute power, signals, and heat across the die surface. By comparison, the face-to-face method creates a flush, mirror image connection between the dies. This chart shows the density upgrade. SOIC-X face-to-face bonding shrinks the interconnect pitch down to a dense 3 micrometers. This scatter chart plots the resulting bandwidth. As highlighted by the blue square, next-generation SOIC-X reaches a die-to-die bandwidth density of 900 terabits per second per square millimeter. While hybrid bonding provides the electrical highway, the conversion of data into light requires looking at the silicon photonics layer itself. This is the foundational layer, the silicon photonics wafer. This schematic shows how optical routing and modulation are printed directly onto the silicon using CMOS processes, achieving a 2 nanometer critical dimension control. Specific components like the micro-ring modulator and germanium photodetector are formed through ion implantation and selective epitaxy. Silicon nitride waveguides are critical here, as they handle high optical power with low signal loss and low thermal interference. These intricate components are not experimental, they are standardized, repeatable building blocks. This grid displays the standardized components within the Silicon Photonics Process Design Kit, or PDK, which allows this architecture to be integrated into standard electronic design automation tools. By mastering silicon photonics at the 2-nanometer level, the industry can now reliably mass-produce engines that manipulate light with the same precision as electrical signals. Zooming out, we can see how these layers assemble into the complete next-generation AI chip. In this architecture, specialized chips, compute, memory, and optics, are placed side by side on a single shared substrate. The memory, compute chiplets, and the new silicon photonics block are all physically tethered by a massive active RDL interposer, acting as the communication bridge. This configuration allows optical data to be launched directly from the package, eliminating the need for separate modules. Placing the optical engine millimeters from the GPU die bypasses the 40-megawatt power penalty introduced by traditional networks. This architecture provides the roadmap for scaling into the late 2020s. The 2027 roadmap targets system-on-wafer, a paradigm that treats an entire silicon wafer as a single wafer-scale processing unit. Moving to system-on-wafer is projected to yield a 40-fold increase in clustered compute power. This growth is only physically possible because of the improvements in energy efficiency granted by co-packaged optical interconnects. The future of AI scaling requires mastering the flow of light through silicon to feed the world's largest computing clusters.